Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel. Today's topic of discussion is converting complex numbers from polar format to rectangular format. Our objective is to learn how to convert complex numbers using polar format to an equivalent rectangular format. This lecture is predicated on the assumption the viewer has watched the complex numbers rectangular format, complex numbers polar format, and complex numbers rectangular to polar conversion lectures available at the Big Bad Tech channel. If you haven't watched these lectures yet or only dimly recall their contents, please take the time to do so now. If you recall, in the aforementioned lectures, we learned to express a complex number using rectangular format as a pair of numbers, a real horizontal x component plus or minus an imaginary vertical y component times j. Additionally, we learned that a complex number can alternatively be expressed using polar format, including a magnitude z acting at a specific angle, theta. Rectangular format is especially well suited to perform the acts of addition and subtraction of complex numbers, whereas polar format is especially well suited to perform the acts of multiplication and division of complex numbers. The obvious problem with our arrangement are those occasions in which we are presenting complex numbers in rectangular format and asked to perform multiplication or division, or, just as problematic, presenting complex numbers in polar format and asked to perform addition and subtraction. While these techniques are possible, they're cumbersome and unwieldy. A far better means of performing the desired functions is to first convert the arguments into a format suiting the desired function, and then performing the necessary actions. If the final answer must be expressed in a particular format, one can always reconvert as desired. Today we'll limit ourselves exclusively to the act of converting complex numbers expressed in polar format into an equivalent rectangular format. Complex numbers using polar format utilize a pair of numbers. 1. The magnitude, z, and 2. The direction, referenced as an angle from the positive x-axis, where counterclockwise rotation is defined as a positive angle and clockwise rotation is defined as a negative angle. The magnitude can be thought as the hypotenuse of a right triangle formed of a horizontal adjacent and vertical opposite leg. The angle can be thought of the angle formed by the hypotenuse and the horizontal adjacent side. The real horizontal x component and the imaginary vertical y component of the equivalent complex number expressed using rectangular format can be respectively envisioned as the adjacent and opposite sides of the same right triangle. The act of converting between complex numbers expressed using polar format to an equivalent expressed in rectangular format can therefore be thought of in terms of basic trigonometry. Let's examine the means of determining the horizontal real x component first. Given the adjacent leg of a right triangle is the product of the hypotenuse times the cosine of the angle formed by the hypotenuse and adjacent side, it can be said the horizontal real x component is the magnitude times the cosine of the angle. X equals z cosine theta. Now let's examine the means of determining the vertical imaginary y component. As previously, given the opposite leg of a right triangle is the product of the hypotenuse times the sine of the angle formed by the hypotenuse and adjacent side, it can be said that the vertical imaginary y component is the magnitude times the sine of the angle. Y equals z sine theta. It should be self-evident that complex numbers in polar format with angles between 0 and positive 90 degrees place us in the first quadrant and should always result in a positive horizontal real x component and a positive vertical imaginary y component. Complex numbers in polar format with angles between positive 90 degrees and positive 180 degrees place us in the second quadrant and should always result in a negative horizontal real x component and a positive vertical imaginary y component. Complex numbers in polar format with angles between 0 and negative 90 degrees place us in the fourth quadrant and should always result in a positive horizontal real x component and a negative vertical imaginary y component. And finally, complex numbers in polar format with angles between negative 90 degrees and negative 180 degrees place us in the third quadrant and should always result in a negative horizontal real x component and the negative vertical imaginary y component. Let's try some illustrated examples of conversion from polar to rectangular format. Given a complex number expressed using polar format as 6.4 at an angle of positive 29.7 degrees, let's express it using rectangular format. Note this angle places us in the first quadrant, and we should expect a positive horizontal real x component and a positive vertical imaginary y component. Let's determine the horizontal real x component first. 1 determines the horizontal real x component of the equivalent rectangular complex number as the magnitude times the cosine of the angle. Substituting in our given values, we find a horizontal real x component of roughly 5.6. Now let's determine the vertical imaginary y component. One determines the vertical imaginary y component of the equivalent rectangular complex number as the magnitude 6.4 times the sine of the angle 29.7 degrees. Substituting in our given values, we find a vertical imaginary y component of roughly positive 3.2. 6.4 at an angle of 29.7 degrees is positive 5.6 plus j 3.2.